Okay, so today we're going to talk about deadlock, specifically resource allocation denial and the banker's algorithm. So let's start off by talking about theory. For a process to run, it needs resources. These can be input-output channels, memory, interrupts, lots of things, both reusable and consumable. The problem is that the number of resources present is limited and is usually much less than the total that the processes need. Because of this, processes share these resources. But there are dangers in sharing, and one of the biggest ones is deadlock. In deadlock, two or more processes are unable to continue because each is waiting for the other to do something. Let's take a simple example. Let's say that I'm drawing a picture and you're writing a midterm. I need a pencil to draw and a pen to outline my picture. You need a pen to answer the long answer questions and a pencil for the multiple choice Scantron. Between the two of us, we have only one pen and one pencil. I took the pencil and finished my sketch, and I'm now waiting for my turn with the pen. In the meanwhile, you had taken the pen and finished your long answer question, and are now waiting for your turn with the pencil. However, neither of us will give up our utensils until we have the other. Here, we're in a deadlock, both unable to finish our assignments because I'm waiting for you to give me the pen, and you are waiting for me to give you the pencil. For deadlock to be possible, three conditions must be present. The first is mutual exclusion, which means that only one process can use a resource at a time. In our example, only one of us can use the pencil and only one of us can use the pen at a time. The second is hold and wait, which means that a process can keep holding its allocated resource while waiting for another. I keep holding my pencil until I get the pen. And the third is no preemption, which means a resource cannot be forcibly removed from a process. Neither I nor an invigilator can force you to give me the pen. These three conditions are all necessary, but not sufficient for a deadlock. One more condition is required, and that's circular wait, which means a closed chain of processes that must exist so that each process holds a resource that the next needs. In our case, I'm holding the pencil that you need, and you're holding the pen that I need, and neither of us can do anything else without each other's utensils. So that's deadlock. And now how do we deal with it? In one of three ways. The first is prevention, which is where we prevent deadlock by eliminating one or more of the four conditions that I just talked about from occurring. The second is avoidance, which is the focus of today. Here we dynamically make choices so that deadlock is never reached. And the third is detection, which is taking action when a deadlock is detected. And now let's go into more detail on deadlock avoidance. There are two approaches, and the first one is process initialization denial, where a process is simply not started if its resource request might lead to deadlock. The second is resource allocation denial, which is what we'll focus on. Here, process's next resource request is not granted if it might lead to deadlock. This is checked using a strategy called the banker's algorithm. Basically, what we're going to be doing is tracking all the resources with respect to each process in the system at a given time. An important concept here is the state of the system. The current allocation of resources to the processes involved is known as the state. The state is said to be safe if there's a way to allocate resources to all processes without leading to a deadlock. In other words, if all the processes are able to run to completion after a series of resource allocations, the state is safe. Whether state is safe or not is determined by the banker's algorithm, which we'll go through soon. And if it is, this means that a deadlock will not result, and so the current resource request by a process can be granted. If not, the resource request is denied, hence the name resource allocation denial. So how does this work? Let's see. The most important thing in deadlock avoidance and the biggest disadvantage is that the future process resource request must be known in advance. And to maintain the system state, we're going to be using 5 matrices and vectors to track it. So these three must be given. The first is a claim matrix, which shows the maximum requirement of each process for each resource. So in this matrix, we can see that process 0, for example, needs 9 instances of resource A, 5 of resource B, 5 of C, and 5 of D to run. The second matrix is a current allocation matrix, which obviously shows the current allocation of each resource to each process. So at this time, process 0 holds 2 instances of resource A, 0 of B, 2 of C, and 1 of D. And here is the resource vector, which shows the total amount of each resource in the entire system. So all resources at any given time need to either be allocated or available, which leads us to the availability vector. This shows the number of each resource that is available or not currently allocated to any process. It equals the total number of a resource minus the current allocation of that resource. For example, the number of instances of A available is 15 instances total minus the total currently allocated, so 2 plus 4 plus 1 plus 1 plus 1, or 9. So 15 minus 9 equals 6 instances of A currently available. Finally, the need matrix. This shows the process's claim for each resource minus its current allocation for that resource. So for instance, process 0 needs 7 instances of resource A, since it requires 9 and is currently allocated 2. 9 minus 2 equals 7. Once a process runs to completion, it will let go of its resources. So these resources will then be added to the pool of available resources. In a safe state, all the processes will run, which means that the available vector will increase after each process is finished, until eventually the resources available will equal the total number of resources of the system. So that's the theory behind Banker's algorithm. Now let's do a problem to consolidate all of this. So here's our problem. The current state of a system with 6 processes, P0 to P5, and 4 resource types, A to D, is as above. The claim matrix, the current allocation matrix, and the resource vector are given. So calculate the available vector, B, calculate the need matrix, and C, see if the current state is safe, and if so, show a safe sequence of processes, and also how the available vector changes as each process terminates. So let's do it. So first, we're going to start off with part A, which is calculating the available matrix. The total, which is the total resources minus the allocated resources. So for A, it's 15 minus the sum of A's currently allocated. So 2 plus 4 plus 1 plus 1 plus 1, which is 9. So 15 minus 9 equals 6. Likewise for B, 6 minus 3 equals 3. 9 for C, 9 minus 4 equals 5. And for D, 10 minus 6 equals 4. So that's part A. And now let's go to part B, the need matrix. P0's claim for A is 9, and its current allocation is 2. So like we said before, 9 minus 2 equals 7, still needed. P0's need for B equals 5 minus 0, so all 5. For C, it's 5 minus 2 currently allocated, so 3 still needed. And for D, it's 5 minus 1 equals 4. Likewise, we're also going to do process 1 in a similar way, and process 2, and the rest of the need matrix as well. So that is our need matrix. Next, we're going on to part C, which is going to be the longest part, and we're going to check for a safe sequence of process runs. To do this, we need to see if there's a process that can run given the limitation of the availability vector. There are 6 instances of resource A available, so a process that needs at most 6 resources of A can run. P0 needs more than 6 of A, as we can see, so it cannot run. Likewise, P2 cannot run because it needs more than the 3 of B that are available, and same logic for P5. So any of the remaining 3 can run, and I'll choose P4 arbitrarily. So P4 runs, and after P4 is finished, all its allocated resources are now available, so we add them to the availability vector. 6 of A from before plus 1 of A that is now available after P4 is complete equals 7 of A. Likewise, B becomes 3 plus 1 equals 4 available. C equals 5 plus 0 equals 5 still, and D also remains 4. In the current allocation matrix, P4 will now not be allocated any more resources, as we can see here. And now that P4 has run, we look at what can run next. P0 still needs more of B than is available, so it cannot run. Any of the others now can, and I'll pick P5. After P5 runs, one more of A becomes available, B stays the same, and C and D's availability each increases by 1, which becomes 8, 4, 6, and 5. Now P5 and P4 have run. P0 still needs more Bs than are available, so it still cannot run, but any of the remaining 3 can, and I'll choose P3. After P3 runs, the availability vector becomes 8 plus 1 of A, 5 plus 1 of D, and B and C stay the same. Again, P0 cannot run, so now we choose P2. After P2 is finished, it releases its resources, and the availability vector increases by 4 of A, 1 of B, and 2 of D. C staying the same. Now the available matrix is high enough for either of the 2 remaining processes to run, and I'll arbitrarily choose P1. P1 runs, and then it releases its resources, which is 1 of B, C, and D, leaving us with 13 A's, 6 B's, 7 C's, and 9 D's available. Finally, P0 is the only one that's left, and it runs because it can. And when it releases its resources upon completion, the available matrix is 15, 6, 9, and 10. At this point, all of the processes have ran without deadlocking. And the final available vector equals the original total resources vector, as I mentioned before. And we determined a safe sequence of events that does not result in deadlock. And that is the processes running in the order P4, P5, P3, P2, P1, P0. And that is all. If you have any questions, please let me know. Thank you for listening.